Okay, material for the final has some overlap with materials that we had for the midterm, but it doesn't cover the whole semester. So we start at a network flow, which we saw in a few ways. We saw how to handle it as an LP, and we saw Bellman-Ford algorithm, Ford-Falkerson algorithm to solve it. We did not see Edmond Karp. I just mentioned something about it, but it wasn't very formal. That you can get polynomial time for Edmond Karp. Then we have skip list. Don't forget the bound about the probability of seeing a really tall skip list. And a hashing that you had earlier. This time it includes Bloom filter. Yeah, and everything that we covered so far, including what we discussed today, which is a primal dual in linear programming. People, any questions? Graded homework, what was it, homework 5, homework 5, some people, for the question of parsing a sequence of words, that I want to break into two words, in the question of breaking a sequence, parse a sequence, a string into a sequence of words, I saw various solutions that really try to make the table a two-dimensional table. And it's not always the case. It's examples that you really overkill by doing so. And in some cases it leads to bugs, in some cases maybe, I didn't always check it all there. It was, maybe there is a way to make it clear, but you know what the solution. We are saying that C of I is true. If I just want to ask, can I parse the whole thing? Or, let's also even harder question of parse it to a maximum number of words. So you'll say that C of I equal the max number of words that S from what dot I could be parsed into, and minus infinity if not parsable. Right, because you cannot leave any characters blank here. So you cannot parse it. So you say C of I, and that's, I took a few points, very few, but just to pinch if you didn't tell me what is C of I exactly, because I asked in the instructions when you're using dynamic programming, what is cell I or cell ij or cell ijk in 3 dimension? What does it's solution to some sub-problem, but tell me exactly to which one it is. And same applies for the final. And now if I have this Cij, then I'm doing for I goes from 1 to n. I'm trying to check the string that contains the first I characters, and now for j goes from I down to 1. If S from I to j is in D, and C of j minus 1 is parsable, is larger than minus infinity, implying that is S from 1 dot j minus 1 is parsable, then what would you do? Then C of I equals max of C of I or C of j minus 1 plus 1. That's it. So only 1D question. So in this case of the hello world, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm standing with I on the D. I'm staying with, let's start. If I'm stating if I equals 9, I equals the L, then probably WORL, I hope, is not a word in English, so I will not pass the first test that check if a string is in the dictionary. SIJ meaning is in D was how I phrased in the question, that you check if a word is in the dictionary. If you just said check if a word is in the dictionary, you didn't lose any point, it was fine. Let's check if the word that start at some j all the way to some j all the way to from j to I is a word, and if it is a word, then you want to ask, is everything that happens before this word, in this case the hello, is it parsable? I mean, which goes from 1 all the way to j minus 1. Large enough? Should I copy it larger? All the way from 1 until j minus 1. Is this parsable? If yes, then to how many words? If I shoot for the number of words. In the question itself, I just ask if it is parsable or not. That's a code that will give you. And yeah. And then you just say that C of I, the number of words that I passed everything from 1 up to I, is the maximum of what was C of I before. C of I before was for various values of j. So what was it before? And what I'm getting by taking the maximum of words that I was able to parse from 1 up to j minus 1 plus 1 because I just added one word. So for the final, play with this if every word has a different cost, depending on, I don't know how likely it is to be used. Okay. You had a question about edit distance when you had events, and I ask you what the maximum likelihood probability, and some people gave a full and very accurate answer. Some people decided that they are going to the log likelihood, which is also fine. Some people just used it as a product of events, but essentially probability that something happens, if you have a sequence of independent events, it's just the product of the individual probabilities. Like the probability that this typo happens times the probability that this typo happens. And what I guess is the reason for it is that we used to think in the edit distance that if I typed A and you see A, then there is no penalty about it. But it's a bit of a lie. If there is a probability that you'll move to each other words, then the probability that you'll see an A and you typed an A is smaller than 1. But it still should be higher than the probability that any other event happened, that the typo happened, if you want to. Okay, questions about it? That's the type mistakes that I saw. Let's continue with primal dual in LP. So just to remind everybody, primal dual, we had a matrix A. We looked for a solution to the problem, maximize C times X, C is another vector given to us, such that AX is smaller or equal than B. It's smaller or equal between vectors here, obviously. So the first row of A, the first row of A times X, X is a stick, dot product X should be smaller or equal, there should be smaller or equal than the first value of B. And the second row of A times this vector X, so smaller or equal than the second value of B. And so on, and all the X's are all zero, are all non-negative. That was a primal. And in the dual, I picked the vector C and I picked the vector B and switched their order, which means they don't have to be of the same length. But now I maximize the same A, but Y dot product A instead of A dot product X. That is, now I take a linear combination of the column of A. Okay, linear combination of the column of A requires it to be larger or equal than C. Where did C come from? It's the same C that was the cost function of the primal. And YA is larger than C. And what do I want to, what my cost function, I'm not maximize, I minimize. If I was minimize here, then I switch to maximize. Y dot product B. Okay. And we saw a few results about this primal dual approach. We said that if I look at the solution, X is a solution to primal, X is X star is opt solution to the primal, then in general I will have an X lives in RD, X lives in RD, then X should be, then X star is on exactly the boundaries of the half planes of A. That is, when I wrote it over here, I wrote it as AI dot product X is smaller or equal than BI. But if X is optimum, then it will satisfy exactly D of these constraints. And now I can take only these constraints that are tight. Here in the slide, I'll assume that it's the first D. And it's much easier to see it geometrically. Here are all my constraints, half planes in this case, because D will be 2. There are n of them, but if that's the optimum solution, I will be on exactly 2. And for my theorem right now, I'll assume that it's exactly 2 and not on, in general, depending on the cost function, you know, it could be less than D, but definitely not more. Okay, and I take, and the moment that you'll show me say that the ones that are taught, that are tight, are that AI x star equals BI, not smaller, but equal of BI for I goes from 1 dot dot D. That would be the first two. Say in our little demo, it was age 1 that was taught, and age 1 that was tight, and age 2 that was a cost function, and I assume that this vertex is the optimum. So I define a new matrix, a bullet which was consist of only these lines, A1, A2, dot, 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 A, D. And I can now find X star, because X star would be, well, I know what is X star, but just to tell you what it is, if I define the B bullet as B1 all the way up to BD, only D constraints. So A, by the way, is a square matrix. It's D there, D times D. X star would be what? I want, if I want AX to be smaller than D, and I told you that it's the on D of them exactly, then AX star is, if AX is smaller or equal than B, and it's taught for D of them, then is that A bullet X equals B bullet, or X star is just a minus 1 of B. And there is a minus 1 because otherwise my solution would not be unique. I need them to be, I need the solutions to look at different directions. And it also gives me now a way to tell you what is Y bullet. Y bullet, if I want Y bullet A to be equal to Y bullet equals to C, then Y bullet equals C A, it's A bullet, sorry, it's A bullet minus 1. Okay, so once you told me what are the taught, which constraints are tight, I can generate both the primal and the dual very easily. The solution to the primal and the dual very easily. Now I'm missing some components from Y. Y is a long vector. Y here is a long vector, but Y has one constraint, Y has one value for every half planes in A, not in A bullet. There are only two, only B. It's on A with a full rank. So Y is much longer, so Y vector would be start by writing Y0, or Y bullet, that will take the first D constraints, and the remaining constraints, and minus D, you'll just write 0 for all of them. And we saw that one of the strong conclusions of this theorem was that any feasible but not necessarily opt of primal, let's call it X, and every feasible solution to primal y. What can I say about them? That in the primal, I'm trying to maximize. In the dual, I'm trying to minimize. But the cost function from the primal, which is Cx, would be smaller or equal than the cost function of the dual, which is By. That was a weak, that was the where did it go? Yeah, that was the weak duality theorem. And the strong duality theorem said, hey, if I just pick the, if it happens that X is the optimum solution and Y is the optimum solution, each one to its own problems, then not only that this is larger than this, but they're actually equal to the same value. Okay. We talked about mean cut versus max flow, that these problems are dual to each other. And let's see one application to graphs before I showed you how to, before we are getting back to graph, to column generator. So I can represent graphs, undirected graphs, in various ways. I can represent graphs in various ways. I can use matrix where if I have I have one row for every VI, one row for every VJ, one column for every VJ, and if there is an edge from VI to VJ, then there is one in the corresponding. That's not a representation that I'm using now. Here I'll use a different representation that will go as follows. You give me some graph. This graph that I'm generating in this example, let's build it. It has 4 vertices, V1, V2, V3, and V4. And in this matrix, it's completely accidental that the number of rows, that the number of edges equals to the number of vertices. Completely accidental for this matrix. And I'll have one row for each one of the vertices. So I have n rows in general. And I have one column for every edge, E1, E2, E3, E4. And if there is a 1 at some entry of this matrix, then it means that VI is on the edge EJ. A 1 here will mean the vertex VI is on the edge EJ. So what happens in this graph? Hopefully, didn't check it yet. But if it works, then I'm looking at the edge E1. The edge E1 has 2 endpoints, one with V1, one with V2. So E1 will be between V1 and V2. This is E1. E2 will be between V2 and V3. That would be E2. E3 will be between V1 and V3. And yet another edge that goes like this. That's E4. Between V1 and cannot be type of 3, right? Between E1 and E4 is between V1 and V4.
How is E1 also connected to V4? Like, should that...
E4 is connected to V1 and V4.
Yeah, but the matrix has in the E1 column, it's a 1 or...
E1 should be, yes, yeah. The E1 should connect to E1 should connect to E1 and E2. To V1 and V2, and you complained about this one. Good?
Yes,
yeah.
Makes more sense.
Yeah, can take it that in every set of slides there is an odd number of bugs. It's like, so everybody understands the matrix here, and now I'm writing a strange LP problem, maybe LP, maybe ILP. I want to maximize 1 times x. 1, sometimes we'll write 1 vector, it's just a vector of 1, 1, 1, 1, 1. We'll use this vector quite a lot, times x, and x lives in, here I want to refer to the set of, I want 1 vertex, 1 xi per edge. In this case I have 4 edges, it's also number of vertices, but it's accidental. So it's in R of the number of edges, such that mx is smaller or equal than 1 vector once again. Here it's 1 row per 1 row per vertex. So this one lives in RV, sorry. That is 1 constraint per every vertex, and x larger or equal than 0. So this problem will make a bit more sense if I'll also tell you that x is an integer. So let's assume that x is an integer, which, as you easily verified, since I required x to be all equal to 0, then because every time that I hit an element, it's with an element of n, which is either 0 or 1, and the sum should be less than 1 altogether, then every xi is either 0 or 1. And what is a graph problem that x will solve? I'm looking at V1, and I'll say for V1, x1 times the element of V1, which is 1, x1 times 1, plus 0 times x2 plus x3 plus x4, and this number should be small or equal than 1. For V2, we will have x1 plus x2 smaller or equal than 1, and so on, and I'm trying to maximize it. So for every edge, every vertex, I had such a constraint, and if the sum of these numbers is smaller or equal than 1, they are all positive, they are, let's say, even all integers, then what does it mean? From all the edges, there is a variable here for every edge, and out of all the edges that connects to V1, which are E3, E4, E3, and E2, you can pick only one of them. Look at the edges that connects to V1. This constraint says you can pick only one of the edges to some solution out of all the edges that connects to V1. So you can pick either E1 or E3 or E4, but you cannot pick both E3 and E4. And the same goes for V2. Out of the edges that connects to it, you can pick only one. Same goes for V3, the same goes for V4, but V4 will not be the bottleneck here. So we played with this problem quite a lot.
Vertex cover?
No. I'm trying to maximize. The vertex cover I'm trying to pick as many, vertex cover I'm trying to minimize how many edges we want.
This is just maximizing the number of edges or number of vertices using only one edge per vertex. So like making it into a line, I guess?
I'm picking a subset of edges with the property that for every vertex, I mean, let's assume that this graph is bipartite, then you'll all see it. Let's assume that this graph that I started with is actually bipartite, which is, if you think.
You're picking a pairing between like nodes in A and nodes.
I'm picking a matching. What was the rule about the matching? So that for every vertex, you can pick only one edge that connects to this vertex. So this problem with the ILP is just a matching. Let's look at the dual. Minimize B times minimize by and B is again, B here in the dual, B here in the dual is the same C that I used in the primal, which are all 1, 1, 1, 1, 1. And now I have one variable per vertex, not one variable per edge in the dual. And I'm trying to minimize something, but what is my constraint? Since I multiplied by, since now I multiply y times y, something should happen for every edge. For every edge, let's look at the edge E1. What are its constraints? Y1 times 1 plus y2 times 1 plus 0 should be, and in this case, notice primal and dual, the direction of the inequality switched, large or equal than 1. So now is your time to say that this is, I mean, you already said the correct answer just for the matching. It's a vertex cover. You want to pick as minimum vertices as possible so every edge is covered. From every edge, for each one of the edges, at least one of the two vertices that are connecting to this edge must be picked. Now, this claim is true for between primal and dual always. That's a weak duality theorem. every solution, integer, not integer, as long as it's feasible, any solution to the primal is smaller than any solution to the dual. That is that for vertex cover, you need vertex cover, you want to pick as few vertices as possible. Matching, you want to pick as many edges as possible. The maximum number of edges that you can pick is smaller than the minimum number of vertices that you need to cover the whole graph. I don't think that it's the only way to prove it, but it's a way. Okay, we talked about column generation. We saw a few. We started to see example where we just said, like in the art gallery question, we want the whole polygon to be seen, but I don't want to pick the whole polygon, the whole as witness point as the whole polygon, so I'll just pick a subset of the vertices. We did it in the last class. And we talked about the cutting stock. In the cutting stock, we had long boards that of length 15 feet from every such stock, we call them a stock. Every such stock I can cut according to one of the patterns. I have a cutting pattern, for example, 2, 1, 0, or A4 equals 2, A6 equal 1, A7 equal 2, would means, well, in this drawing, this cutting pattern will means you can cut it into 3 boards of length 4 and 0 boards of length 6 and 0 boards of length 7. Like this cutting pattern will means, this highlight cutting pattern will means this is 15 feet and I can cut it into 1 board of length 4, another board of length 4, and 1 board of length 6. And I still had some, and presumably I still have some left over. Okay, and I can generate all these columns, all the possible ways, all the cutting patterns. And to remind you the problem in general, people that I think that few of you were not here last time, the problem was decide buy as few boards as possible, buy as few stocks, sorry, as possible. You're manufacturing board, you're buying stocks. Stock is just a long board of length 15. You want to sell, there is an order for 84 feet boards, 56 feet, 107 feet boards. So what do I do with this cutting pattern? I want to decide how many of the boards will I cut based on pattern 1, which I'll define as x1. x1, how many boards are cut based on pattern 1. x2, how many boards are cut based on pattern 2, dot, 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 all the way up to as many patterns as I have. And I'm trying to minimize the sum of the xi's, because every long stock of 15 boards cost me $1. So I'm trying to minimize sum of xi, subject to m dot product x, which means the first row here will say, if you're cutting x1 units into 3, you're getting 3x1 many boards from just this part, plus 5 boards according to this pattern, then from each one you'll get exactly 2, and the order is to get at least 80 boards of length 4, and 50 boards of length 50, and at least 100 boards of length 100. Okay, so we can solve the LP already. Deeply hurt, I left here 2 monsters yesterday. Yeah, okay, but of Of course, the number of patterns that I have for cutting this ball might be exponential. So that's what I want to target right now. And want to tell you about column generator. So first, what will be my primary problem? Minimize the sum of the xi. Remember how many bolts do I cut according to pattern I? That's a xi. Minimize the total sum. So the vector C here is just 1, 1, 1, 1, 1 according to the pattern, but might be extremely long, a lot of pattern, such that M dot product X is larger or equal than B. That is, you'll get at least 80 bolts of length 4, at least 50 bolts, etc. for rank 6, and that's a primary. The dual is a bit strange. At which dimension the dual lives? Well, since I only have 3 rows here, then Y lives in 3 dimensions. I want to maximize Y times B. What is B? Help? The same B that I was here. The 80, 50, 100, such that Ym is now smaller or equal than C. What is C? The same C that I was here, all ones. 1, 1, 1, 1, 1 for each one of these columns. And I realize that there is way too many columns over here. Here it was with just cutting pretty short stocks into pretty short, very few subset of balls. Of course, I can increase, and then there could be way too many patterns. So I'm trying my luck, and I'll pick out of these 3 patterns, out of all the patterns that you see here in the pattern matrix, I'll pick just a few of them that I think that maybe I'll do with only these patterns. And column generation will say, start by picking only few columns. You need to pick at least D if you live in the D dimension, but maybe you can get away with only D, and empirically, we will tell you via primal dual if you need more patterns that will improve your solution. You can solve optimally the constraint problem. The constraint problem, I'll start with only very few columns of the matrix. Very few patterns, and if needed, then I'll add more patterns and resolve the LP once again. So that's where we are going to. So let's pick as M prime, that's type of the L here. Let's solve as the LP problem, but when M prime is just the first 3 columns. 3, 0, 0, 0, 2, 0, and 0, 0, 2. Okay, and I want to find a Y here that satisfied it. I looked at the LP solution right here, and what do I need to do with it? I decided both for the primal and for the dual, it would be, in this case, very easy to compute the solution because, remind everybody, M prime hopefully has an inverse, namely M prime minus 1. And if they do, then the dot product should be 1. But because the solution is, this matrix is so friendly, hopefully you all see what is the inverse of M prime minus 1, which is, help?
The inverses of the entries, so 1/3, 1/2, 1/2.
1/3, 0, 0, 0, half, 0, and 0, 0, half. Again, so far you don't know why am I insisting only on this problem, but here is intuition. Possibly this matrix is enough, possibly, no, in this case it will be. I will have to add more columns from it. Now, if I want to solve the primal problem, I don't get anything, I don't get any money from solving the dual. But what do I study from the dual? Looking at the solution, let's look at the solution for the primal. Solution for the primal would be, how we say it, would be y, which is, what was it? Y, which was, we need at least 80, 50, 80, 80, 50, and 80, 1500 times, doesn't matter for this matrix, this m prime minus 1, which gives 80 divided by 3, 50 divided by 2, and 100 divided by 2. So this will be my vector y. Right? Because I want to say that, that would be my vector x, sorry. That would be my vector x prime, but only for the constraint problem. Why do I call it a constraint problem? Because I'm not using all the columns of A, I'm just using the columns of A that I decided to pick so far. And that would be x prime, and I have no clue whether I can improve upon it or not. If I have all the exponentially many columns, then I can ask, do you know or do you know? But on the other hand, let's create the solution for y prime, which is what? M prime minus 1 times C. M prime times C, it's actually from the other direction, but it doesn't matter. So times 1, 1, 1, which is, in this case, third, half, half. So let's think about what do I have so far. Here is, I'm solving the problem of y dot product y dot product m, or I think that it will be a bit easier to think that it will be a bit easier to think about it as here is m transpose times y transpose. Just change the order and multiply. What I am, and I want it to be equal to, for each and every value, small or equal than 1. Now, that's what I really want to solve, but it's exponentially. So instead of solving it for the whole m, I just solved it for this matrix m prime over here. M prime and m is the whole thing, including all the constraints that I added. If there is some meaningful constraints that I added, where will it appear? It will appear as one of the columns here, which will be one of the rows. That's what it's called. One of the columns here, or one of the rows here. It's the same element. Just here, it's sitting down. That's why it's called column generation. What do I know about these columns? Why? I found this y star. If y star agrees with all the constraints that are written in the whole of M, then Y star is also the optimum solution for the non-constraint dual, which will make X star an optimum solution for the unconstrained problem, and that would be my sign to that I'm done. I don't need to solve it anymore. When will I find out that that I missed one of the constraints? Well, in the constraint problem where I failed one of, what is this here? It is one of the patterns that didn't make it to M prime. If I left one of the patterns that did not make it to M prime, then when I'll take this one multiplied by Y, it will be larger than 1. Am I? Yeah.
So you calculate a Y using M prime, but then you run Y against the M constraints, and then if it's wrong.
So my problem now is not the problem now is, can I find, given that usually we're looking for either X or Y, my problem now is I already know what is Y, that is Y prime star, that is the optimum solution, but only for the constraint problem. What am I asked next? Are there any pattern that I should have taken into account? Because if that is, can I find values of A4, A6, A7, that is how many boards do I cut, such that altogether, when you multiply them, A4 tells me how many boards of 4 times A4 plus 6 times A. How many boards you can come to 6 plus 7? How many units of A7 you're getting? It will still be smaller or equal than 15. But so far, to satisfy this part, take all of them as 0. And in addition, it will Y, this solution that I had in mind so far, times this one more columns that I need to generate will be larger than 1. Here is Y star, third. And to start with, I want to say, hey, there are a lot of constraints here that I didn't use, so let's just check them directly. It is true that all of these are legal cutting plane to cut according to a new. These columns, the result of the cutting fits into 15 boards. So do you see any column here that when I multiply this column by Y, it will be larger than 1? Remember, Y star so far is third, half.
2/3 plus 1/2. So in the fourth, or fourth or fifth, both of them are bad, right?
What do I have here? If I take this column, M5, the fifth column of M, times this is Y star, which is third, half, equals to 2 times third plus 2 times third, 2 of third plus half, larger than 1? Yes. This is larger than 1, so it is a violation. Again, everybody understood why I needed to switch to the final, because in the why I needed to switch to the dual. In the primal, nothing told me about these columns that it's very specific without looking at it directly. I had to check each one, which I also have to do in the panel, but the panel somehow, it presented itself because I had a violation to the constraint. Okay, so what are we going to do next? In this toy example, so that would be my next endpoint. Solve both the primal and the dual. Actually, at this stage, solve only the dual. And see now, and at this point, you wouldn't get any violation, so that's an optimal solution. But so far, I didn't prove anything that is much better than doing it already with all the variables. Well, you're getting something about using fewer variables, but so far it's not really that amazing. But what can we ask about it? Here, remember the problems that we discussed exactly a week ago in dynamic programming. The stop cutting asked, you have a cost. You have a cost of order of how many units of length. 4 do you have? Cost of how many, how much how much a board of, now I'm changing cost of each individual board, or how much can I sell it, each individual board. I will get for a board of length 4, whatever Y star told me, the original Y star. Y star told me on a board of length 4, you're getting $1/3 of a dollar. On a board of length 6, you're getting $half, and on a board of length 7, you're getting $0.50. And now your problem is within a stock of 15 feet, find the best way to cut it to get pieces out of it so you'll get the maximum price. Which we did when we assumed it all, when we looked for the dynamic programming program for this. We assumed that all the pieces, that every set is used at most once, but of course I can multiply the same set a few times out there. So it's the same dynamic programming, will solve it for me, and all I'm asking is that can I cut a 15-seat board in this way? Okay, so even if I don't have all the columns of the matrix M ahead of time, instead I will use the knapsack problem. That's exactly the knapsack dynamic problem that we solved with dynamic programming. It's NP hard, but we said when all the lengths are integers, we can solve it, and if they are not integers in this case, then we can easily approximate it. And that's a very practical method, and that will work. Yeah?
If we're doing the problem like we were a second ago, if we go back just one slide, because our matrix M violates both patterns 4 and 5, could you solve the LP using just 4 and 5 to see whether those two constraints are equivalent before choosing one to add? Because it would still be a smaller problem, like dimension-wise.
I think that I'll try to put it out there. When I worked on it for some research problem, actually the ones that I'll show you in the next slide, then we played with various instructions, heuristics like, is it best to take the ones that violate once the most, does it really expedite the time? Which you find as different heuristics. But yeah. So what did we see so far in this column generation? Column generation, just to summarize what we had so far, instead we had a matrix that we had an LP, at least when we had the whole story. We had a matrix M that is very long, possibly exponentially. We had, if we solve the LP directly, it lives in a very high dimensions, x1, x2, all the way up to x huge. So I don't want to use exponential in many directions. Instead, I will solve the LP, but only for the constraint, the restricted problem, where instead of M, I have M prime. I'll solve both the primal and the dual, and I'll use a very different trick to tell me, hey, you have some column here that you forgot, and if you add it, it will either improve your primal solution, which is what we really want, but the way you discover it is not by improving it, because then you have to check each and every column here. Instead, you can sometimes find it, so it violates one of the constraints of the dual. And in the dual, by the way, worth mentioning it, or it's nice that we have a lot of problems that here in the primal the dimension is very high, but there is only, say, D, much smaller number of constraints. When I'm solving this problem in the primal, and by the way, in terms of difficulty, solving a problem in the primal and the dual is exactly the same. If you have a solution to one, you have a solution to other for the non-constraint. Instead of working in very high dimension, but with very few constraints, I much rather, and that's something to use all over the place, not only with the column generation, I much rather first solve the primal, because here N is very large, but I can still handle, but the dimensionality of Y, the dimensionality of, so I have N constraints over here, which is huge. So, but remember, our linear programming, for example, the incremental linear programming, runs in order of N times D squared. Doesn't care very much, behaves linearly in N, but behave horrendously with dimension. So in the dual, I'll have N, which is very large, but now the length of Y that I'm trying to find is only D, and it's nice. Okay, quick one more example, and we'll call it a course, and we will not have time for local search. So we talked about the art galleries that we solved with ILP. Talked about it at least twice. I have a set of vertices. I want to see each and every vertex here. I just care about seeing vertices. And I want to find minimum number of sensors that I place a sensor in the vertices that I pick. And what will happen is that the point 1 will be seen by one of the sensors, point 2 will be seen by one of the sensors, point 3, and so on for the sensors that I pick. What you see here are the way I picked a constraint x2, x3, and x4 that is larger than 1 is because one of these three vertices, vertex 2 or 3 or 4, 2 or 3 or 4 must be picked in order to guarantee that vertex 4 by itself is seen. Okay. Let's talk about scheduling sensors. I want to talk to you about the problem of scheduling sensors. I don't have a slide for it. That's from this morning, so I am actually.
I think it was the slide before talking about the battery.
Yeah. So now, yeah, it was not fully edited. So the problem right now, and we'll continue on the whiteboard, is every sensor has a battery. I can turn on and off the sensor anytime I want. I want every point here to be seen, or every vertex at least, to be seen by a sensor that is active for each moment, and I want to do it for as maximum time as possible. Make sense? So I need a schedule that would say, for example, a schedule here would mean, for example, turn on sensor sensor 1 and sensor 2 until they deploy their battery. Then maybe turn on 5 and 6 when they die, when they use the battery. Turn on sensor 5 and 4 because they can also see the whole thing. 5 and sensor 4 also see the whole thing, and so on. And I'll keep doing it for as long as possible. So let's see how do I solve it with LP. And then I need this matrix. So ignore everything else besides the matrix. So here the matrix M is defined as 0 and 1s, and every column to this matrix, I'll call it a cover of the polygon. And what does it mean here that it's 0, 1, 0, 1, 0, 0? It means that one of the covers that I can get for the polygon is by turning on sensor 2 and turning on sensor 4. You see the whole polygon. And maybe you want to use it for some time. And then cover for a while sensor 2 and sensor, turn for a while. Here is another cover, here is another cover, and so on. And altogether, I'll have an exponentially many numbers of covers. So a little puzzle for you. Is this clear? You see that the same sensor here might participate in many covers. There is exponentially many covers that I can generate in this way, so it's candidate for column generation. I don't want to have all of them. My problem is, of course, is find, let's call it vector t, which is t1 dot 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 tn, such that t dot product 1 is max, but ti indicates for how long sensor cover I is used. So I want to maximize so T1 will tell me if T1 is half an hour, it means use this cover for half an hour, then use this cover for maybe 10 minutes, use this cover for maybe 30 minutes. Every time that you're switching from one cover to another cover, it means different sensors are active, and possibly you'll turn on and off sensors multiple times. That's fine. Does anybody see a solution that it makes sense that you are getting more time when you have, if you're allowed to turn on and off a sensor more than once? And I need to assume something about the maximum time. Let's assume that the maximum time is 1 hour per sensor. That's what the battery is constrained. If you don't like sensors, then put batteries and you want the whole polygon, put lamps over there, and then the whole polygon needs to be illuminated.
Well, given that they have uniform running times, I would think no, right? because the moment you use, for example, sensor 2 in cover 1, you guarantee that you cannot use all of it for cover 2, right?
So that's a polygon with a hole inside. And I want to create the maximum cover over here. So if it's not exactly what I wanted.
So here you pair B
Here,
and B
here
together.
each one of them will work. So we'll wait with the puzzle. Yeah, there is a similar example that will show that it makes sense to actually use it for half, half, half. But so I want to pull. So I want to maximize this p times 1, the sum, total sum that is all covered, subject to this matrix M with all the covered times the vector t is smaller or equal than the vector 1. That is, each sensor is active for at most 1 hour. So that's a linear programming, but here I don't, I can afford using all the covers in the world, all the possible combination of sensors as long as it's a cover. Okay, but there are way too many covers, so we need to use our ILP. Out of time, we will only use subset of the covers, solve the primal, solve the dual, and now the dual will give us a vector y. And now this vector y gives me some values for the sensors. And now when I have my values for the sensors, I'm going back to this problem of the, remember that was the ILP that I used to find, for example, one cover. Now I have values yi for each one of the sensors, that just like what we saw for the cutting board, values yi for each one of the sensors. I'll try to minimize this value of yi is given, find any cover that minimizes this and is covered. How do I know that it's covered? It should satisfy all of these. So the moment that for this value of yi's, I have a violations for one, or it doesn't see one of the points, I realize, hey, with violation, you need to introduce one more cover to the matrix of covers and solve the LP over there, because I don't mind getting solution right now. But instead of solving the oracle here, the column generation, generate a new one via solving a dynamic programming, which we had in the NEPS problem. Now instead we'll use a version of the ILP. I will massage this slide and put it for you. But essentially it's exactly the same. Idea is the same, a nice example of why column generation is useful. People, completely honestly, I had fantastic time. It's like 5, 6 times that I'm teaching this course. Don't know if you're the best thing over, but definitely in the last 10 years. It was in terms of class engagement, how most people were doing. Interest in the course, I had great time teaching you. Sorry that it came at the expense of you had to suffer from all of it, including the typos. Apologize for it. We'll have reviews before the midterm, as usual. Here I'll publish practice questions, and if you want to improve one of your homework, but let me know, then I'll ask you to submit solution to some of them before that. I cannot officially have a homework. Another homework at this point of the semester, but I can still let you improve your work by answering a few of the practice questions. We'll just have to negotiate what exactly and make it fair. if needed. Otherwise, we are done with homeworks. Okay, thanks. Format is the same. Material as you saw is in the document.
Can I ask a question
Yeah.
about so in so you drew up the two triangles, and it's like you run this for half, you run these two for half. This is a total of 1 here, but then you get to run
Actually, can I just have
these
my
for
all
a half, which gets
Can I
you.
just have my
Yeah, the
And I have
issue
JG.
here is
Yeah,
that
yeah.
here, if I just turn this one on, then it's also a cover. That's why I needed to have one more tweak. But I think that if I have a pentagon, anything with odd number of edges, it will work. But
Well, they're asking if we get a chance.
We should hang out.
Okay.
We should.
Thank you.
You're like actually.
Yeah. It means I actually have like
Very,
very
very
schedulable free
I was
time.
just talking with Jackson. He's like, yeah. Now that instead of school, I have actual job. I have more free time.
If I was you, I would consider if you can work doing that, because what I've experienced is working like a part-time job, which pays more than your like a semester of school. But it's also I haven't done it long enough to know if it's diminishing.
and so yeah, if
No,
I
I
just
feel that.
do this,
Yeah, can we bring
and
6
if now
pages?
I'll pick,
That would not.
No, we're saying we should just have a group.
if I'll pick something like this, then I can.
Knowledge.
I'll zoom it
Group
out.
exam,
Here is my
like in
triangle,
basic, we have to do an NP hard problem,
and
the big brain.
We have to code it too. We have to prove.
I'll add
Yeah.
the
Which
guard
like,
over here
you know, I
sees
feel like
into
if you're
it,
an
a
algorithms
guard
professor, you should
here
put your
and
syllabus
here
like if
can
you can
also
prove that
see
P does not equal P
here
like
I
NP,
indicate
and my name is on it as
but
a
a
reference,
single guard
then it should
will mix
insta like hundreds, like you know what I mean?
so I
Yeah.
need
You want to like
two.
share these.
I feel like at that point.
It's like how
So
universities used to have
share
math
these ones.
duels, where you could challenge a professor for their title as professor.
For title?
Yeah, they used to have that's used to how professors used to be chosen like really far.
Yeah,
If
we're making it so that
two
there's a
people
spot.
like you would challenge a current
This
professor
guy,
and you'd both come to each other with
this
math
one can
problems.
see this
Like
one,
you know, like 20 math problems,
this
and if you
one
can
does
solve
not
more
use
of
this one.
theirs than they can solve of
And
yours,
then you need
you would get their
essentially
title.
to
So
have
like a
at
bunch of
least
professors
three
will
cents. All I
learn,
want is to have three
like
cents of
solutions to
working.
problems
So
and just
if I
not
need at
publish
least
it as
two
their like secret job
sensors,
security.
So you're saying in a situation like.
So like that's what happened with
Trying to find a way
using the
to do
square
it
root of
where-
I, is someone just
I see what
like
you're saying. You're saying this
kept it in their back
parentheses.
pocket, so when someone challenged them, they'd have problems that required using
Yeah.
I,
Okay.
so you can see it by,
and then they would just like get them all
and I
right.
put one of these in each one of the corners, so I can solve it by
It's part of your job.
two
Is that you have
guards
to,
know.
yeah.
at each moment because
And
the
the
guard
idea is,
here
you know,
sees into it,
if someone
and
tries
these
it
two
and you
guards
actually know
sees
your
into
stuff,
it.
and
So
they don't,
the
you're just gonna demolish them.
float one would be
Too much animation.
make
Pairing up
one,
the pairs.
yeah,
Not a lot,
1 and
but-
3 for half hour, yeah.
Another hard problem.
1, 3 for half hour, and 3.
Battle each other.
Yeah.
Yeah.
So for each pair that covers it, you get a half. So you
Yeah.
multiply. Okay.
Yeah,
Yeah,
so
that's
like
what math
for
professors used to do.
homework 5 for the first one, like I've done what you
Mhm.
talked today, but so I guess I also added a pre-processing step to calculate the substance.
Now that I have like very
That's fine, that
predictable,
I wouldn't
I
take
work 8
points,
hours every day.
but what is a
So if it's
BIJ and
not,
how do you use
you
it?
know,
So
I didn't
BIJ is
know.
Well,
basically
I-
like this pre-processed substring so that you can calculate the
Yeah, that's like the
substring.
time, like
So
I'm
it's basically
unavailable,
the
like
string,
at
but like I've added a
kind of
step
deal,
to
yeah.
that.
It's like you're
In
alone.
the
Okay,
main
so,
loop it's
so what is a CIJ?
CIJ is the maximum number of English words in the
Because
substring.
I have
Ask for an
I have a
extension.
test right after this.
You can
You
always,
can start at 8.
yeah,
So
you can
what
always,
is
you
the
can
I
always show up at 9.
in the
That is
CIJ?
So I is basically like the like
So, yeah, come to office hours or
Also, you can move the exam.
come to office hours or at
Because they
least
did all
send
the
me a
math
read
that
rate
like,
and I'll double check.
you shouldn't have, like, the
Thank you.
minimum number.
I have a question in the same question. So
Calculate
you
the
told you have
expected
clicked
number
3
of
of this, but
Yeah.
you have said no runtime and no correctness. There's a correction from the runtime.
Running time appears correctness doesn't.
But
Am I what?
I can't give you homework.
And I also had an issue with
Bro,
the
Adriana's still
correctness,
doing
I think.
I
Yeah, I
know.
thought it was
Savage.
overly
He's so
complicated,
bad,
and
he's
I
straight up
didn't
brutal.
see.
Those
And
110 kids, man.
They need it.
you
They
write
need the
something
brutal.
here, but I wasn't convinced that by
But like, why?
and
I don't even
the
want to do
correctness
that.
that I suggested
Me
was very
either.
simple,
But not
and
really.
right, because all you want to say is C.
It doesn't not work.
If it's true that CJ is correct for all the age up to,
Yeah.
then, and there is another word, then C of I is just
It
one
classes
plus.
are
That's
really
all
like
you wanted to say. Look at the optimal partition, and there
I showed the
is
classes
the
out.
algorithm will find the optimal
Yeah.
partition,
Like,
which you do
he
by that.
preferred us there for quizzes.
I
But
don't
otherwise,
exactly
like, there's
remember
like
what went wrong with this one, and I want to run to my office, so sure.
Thanks.
Okay.
But we're not increasing the number of kids.
Yeah. It's just more sections.
Yeah.